Hi everyone, my name is Chenwei Peng. My research question is optimization of passenger and freight co-transportation in modular transit systems. Firstly, I want to introduce my motivation for studying this topic. Currently, most cities in the world still use traditional public transit systems. Fixed routes and fixed schedules are used in passenger transportation. As for freight, the growing e-commercial sector means there is an increasing demand for small parcel transit within cities. However, there are some problems with the current transit systems. For passengers, if buses have a high frequency of departure during off-peak hours, a lot of space in the carriage will be wasted. If the frequency of departure is reduced, passengers will have to wait for a long time. These two can hardly be balanced, and freight delivery also have a lot of restrictions. So the problem is how to solve the problem at the same time. The answer may be to use modular autonomous units by using co-transportation transit systems. Next, I would like to discuss the gaps in the current literature. Since modular transit systems are still in their infancy, most studies on them focus only on passenger transportation. FRT here means transportation on fixed bus lines, while DRT means transportation can be provided at stations that have demand outside the lines. Although most studies for pure passenger transportation use FRT and DRT transportation modes, combination, most of them are limited in a single line and nearby areas. As for core transportation system, as shown in the figure above, the study only considers FRT or DRT. Therefore, this study considers the direction missing from existing research and combines the two service modes on a network consisting of multiple lines and additional stations, while using the co-transportation modular transit system. This study uses modular automated unit developed by Next, which the technology is currently quite mature. There are some features of this type of vehicle and some assumptions made in this study using this machine. MAV are coupled via MAUs, where MAUs are moving identically in space and time. The same MAU carriage can transport passengers and freights at the same time, and the capacity is 15 passenger units. Four status may happen in one MAU carriage: only passenger, only freight, passenger and freight, and empty. FRT service is provided for both passengers and freight, and DRT service only for freight. Now, I would like to introduce how the space-time network of this study is established. Firstly, we have depots and stops with time steps constitute nodes. The picture on the right shows the possible trajectories of three MAUs and the corresponding status in the carriages. And there are four kinds of arcs together form feasible paths. Demand is set in groups on each arc segment. Passengers have strict time constraints, while freight only needs to be completed within a time window. This mixed integer quadratically constrained programming path-based model solves the routine planning of each MAU. The objective is minimizing the cost of all paths that MAU passes through. Since MAU are autonomous and powered by electricity, we use this form to calculate operating costs. First, the first constraint is path assignment constraint, which ensures that each MAU selects at most one path. Second and third constraint ensure passenger and freight demand volume do not exceed the total amount on the arc. Next two are demand satisfaction constraints, which ensures all demands are met. Then the capacity constraint makes sure that the capacity of each MAU compartment will not be exceeded at any time. Since we don't want to form a group of MAVs that are too long on a road, we set the last grouping limit constraint. Different initialization methods can produce different quality initial solutions, but also have different computational time. We try to use two initialization methods, the groupie solver and the greedy heuristic. To speed up the calculation, not all paths are used. First, some paths contain the demands are selected. Then, for groupie, the result will be the optimal solution of this P demand. The advantage of this initialization method is that all constraints will be satisfied. In the greedy heuristic method, unallocated passenger and freight demands are first represented by UE and UF, then without exceeding the capacity of each MAU. This scoring formula is used to assign all passenger and freight demands. This process will repeat until both UE and UF are 0. This method will cover all demands onto feasible paths extremely fast. Due to the complexity of the model in early testing, the Groovy solver struggled to find a solution within an acceptable timeframe when encountering slightly larger datasets. So the ALNS algorithm with its adaptive mechanism and fast coverages was chosen. The figure is a framework of the customized ALNS algorithm. We have just described how to generate the initial solution. The next step is to determine whether the stopping criteria are met. Simulated annealing is used. When the stopping criteria are not met, the destruction operator is performed first. The operators are divided into two levels, pass level and arc level. If the pass level destroy operator is selected, the pass level repair operator will be automatically matched in the repair phase. The orange circled parts are the weight of the operators, which change depending on whether they have contributed to the improvement of the solution quality in the past. And the probability of each operator being selected is based on the formula of the relative well selection strategy. When a new solution is obtained, even a worse solution may still be selected by comparing it with a random number between 0 and 1 through this probability formula. Next, we conduct numeral experiments on different methods. In a space-time network, adding stations in space and time steps in time both increases the computational effort. To determine the specific impact of varying latitudes on the result, we conducted two sets of experiments. One fixed time step and the other fixed the stations. And because there are different connection methods between lines and between pickup and delivery stops, it is divided into two groups. In the first column of the table, T stands for the number of time steps, L stands for lines, and PD stands for pickup and delivery stops. From the result in the table, we can see that the number of connection points between stations on different lines will cause the Groovy computational time grow exponentially. The reason is that the diversity of paths increases, which leads to an increase in P demand. The greedy heuristic method was also affected, but to a lesser extent due to the lower base. And this initialization method always have a better computational speed. The following is a set of numeral experiments using smaller spatial network with a number of 10 to 120 time steps. The first two experiments demonstrated that Groovy can produce an exact solution, while the other two methods achieved results within an acceptable ranges. It can be seen that the ALNS algorithm with Groovy initialization method is always faster than the greedy heuristic. And the quality of the solution is also consistently better. Therefore, we can conclude that the computational time and quality of the final solution of ALNS algorithm depend on the quality of the initial solution. In the final part of the numeral experiment, we conducted a case study using data from actual bus lines and pickup and delivery stations in a district Shanghai to further verify the feasibility of the model and algorithm in real-world applications. A total of 2 bus lines and there are 4 express delivery points are used. The time is from 8 to 9:30, with first hour being the peak up period and the rest being the off-peak period. During peak hour, bus run every 15 minutes and during off-peak hour, they run every 20 minutes. The figure on the right shows the number of passengers and freight transported at different times. We can see that passenger demands will be prioritized. As the off-peak period gradually approaches, until space began to appear in the MAUs and freight demands began to be processed. This is a key to reducing costs, making the system cheaper than separate transportation system and eliminating the need for 8 MAUs. Even the cost of a traditional bus plus delivery van combination was already 5 times higher in this 1.5 hour case study. Finally, two main conclusion is algorithm for MAU routing problem is effective and the transit system is efficient. ALNS has a huge advantage in computational speed and can achieve acceptable solution quality using 2 different initialization methods. At the same time, compared with MAU's separate transportation system, costs can be saved by 3.9%, and for the traditional public transit system, cost can even be saved by 83.4%. Therefore, passenger and freight co-transportation modular transit system will certainly play an important role in intra-city transportation in the future. Thank you for listening.